We want dy dx. So now it's just algebra 1. You just distribute all the negatives. Oh, you've done already, but you made a mistake. Multiply everything, distribute all the negatives, multiply everything out, move all the dy dx terms over to one side and everything else over to the other, and like divide. Go.
dy dx. Whoa.
I was talking about the next one.
That one is pretty cool. That's like,
Yeah, it's like polka dots. Swiss cheese. What kind of Swiss cheese?
So this becomes
Huh?
3x squared. Is the
I mean,
camera back
yeah,
on?
but it's more like I feel like it's the opposite of Swiss cheese. It looks more like the inverse of Swiss cheese.
Alright, good cheese conversation.
dude, you like?
So great. I love
You know, like monster cheese, but spelled with a U.
You mean Munster?
Yeah, Munster.
Yeah, monster cheese with a U.
Okay.
But is it for real?
I mean, is it not pronounced monster?
It's Munster.
Oh, okay, that's basically monster with a U. Okay.
Alright, who's with me? Attention spans are drifting, so I'm just going to keep pushing on and go faster. You just do that, boom, 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 and then finally, you just divide.
Booyah. Is it?
Alright,
I
so
feel like
did some of
cheddar
you
cheese is
independently
more
get this
American
exact
than
same
American
formula? Alright, I'll take that as a yes. Good. What is this formula? It is a formula which takes as input an ordered pair x comma y on this curve and outputs the slope of the tangent line to the curve. And so, just for purposes of specificity, I have now asked a small follow-up question, which is, hey, what is dy dx at the point 0, 2? You may confirm that the point 0, 2 is on the curve via visual inspection, or by just plugging in 0 for x and 2 for y, and just agreeing that the equation is satisfied, yeah? Okay, so if the equation is satisfied at 0, 2, then that's a point on the curve. What is the slope of the tangent line to the curve at 0, 2? Well, now I just plug 0 and 2 into this formula, and what do I get?
You get 1/2.
I get 1/2. Draw the tangent line to the curve at the point 0, 2. Does it look like it has slope of half?
Oh my god.
Yeah.
Oh my god, is right. Woo! Good. On the back we have exciting things, hyperbolas, folium of Descartes. You have this little weird bubble thing. Okay, you can do that later or never. Go put that away, let's do something else. The last function, I'll call it the last function I guess, that you currently don't know how to differentiate, that are important, are the inverse trig functions. Okay, so take out this packet called derivatives of inverse trig functions.
Which packet?
It's 6 pages long, and it says on the front, derivatives of inverse trig functions. Okay. And also, while I was here at like 8:30 last night, the photocopier was like jamming, so this packet's a little bit messed up, but I didn't have the heart to like throw out hundreds of pages and do it all over again. So the margins are a bit messed up, and it gets like worse later. So sorry about that. But the other thing is, good, for whatever reason, inverse trig functions are like one of the things that pre-calculus students find extremely difficult. And so, oh man. Whew. Okay, and so, I bet a lot of you, like, actually I don't have to bet, because I know, because I keep asking you questions about inverse trig functions on math tests, and you keep getting them wrong. So, here's your last chance to learn the freaking inverse trig functions. We got 9 minutes, let's go. We're going to do one of the 6. But if you repeat this process, then you can finally learn this once and for all. The overall goal of page 1 of this packet is to find the derivative of arctan. Okay, how should we do that? Well, first, this is the way this packet is organized. On the top, please simply graph tan. Okay, I'll give you 30 seconds to make a decent graph of the tan function.
Hey, Arya. You should put that.
Bless you.
Thank you. Okay, is that the graph of the tan function that you have on your paper?
Yes.
Good. All right. What is the problem with this tan function when it comes to taking the inverse? Well, unfortunately, it is not one-to-one. And I cannot take the inverse of a non-one-to-one function. So what I need to do is I need to artificially restrict the domain of this function in such a way that it is one-to-one. And we just have to decide on some way to do that, and there's no one obvious right answer, but there's the way that everyone does it, so that's just the right way. And the way that everyone does it is to specifically select the interval from negative pi over 2 to pi over 2. So just scratch over in like a thicker pencil, or make a box, or do whatever you want to do. You just have to memorize this, if you haven't already, that when we take the inverse of the tan function, we look at the interval from negative pi over 2 to pi over 2. Okay, now that we know that, we can graph arctan. And what is arctan? It's the inverse of tan, using the fact that we've restricted the domain of tan to negative pi over 2 to pi over 2. Therefore, the range of arctan is going to be the domain of tan, and so the range of arctan is just negative pi over 2 to pi over 2. And then you can just kind of plot points, right? Because it's just, an inverse is just reverse the order. So like there was a point pi over 4 comma 1, now there'll be a point 1 comma pi over 4. There was a point negative 1 negative pi over 4 negative 1, so there'll be a point negative 1 negative pi over 4. And then when x is a tiny bit more than pi over 2, y is infinity. So as x goes to infinity, y will go to a little bit more than pi over 2. And okay, who's good? This is just pure pre-calc review. Many of you, like 2/3 of you, just know this stuff cold. Many of you are like, you just guess every time. And you don't know what you're talking about.
Let's go.
Okay, now we introduce a little bit of calculus. Using a pencil as a visual aid, or just using, your imagination, investigate the slopes of the tangent lines to arctan. And on the bottom left corner of this page, there's a space for you to guess what the derivative of arctan should look like. I'll give you 1 minute to make a guess.
I don't know, it's really big in your zero.
Minute to win it.
Really small to get in. I don't know, something.
Less than 1 minute.
Probably that.
What's the slope look like here? Tiny positive, right? And then the slope gets bigger and bigger and bigger. The peak slope is at the origin, but what is that slope, do you think?
1.
Yeah, it's just definitely got to be 1, right? Because the slope of tan at 0 is 1, and this is just the reflection over the line y equals x. So when you flip this tangent line, who's with me?
Move.
Okay, so this is going to be 1, and then what happens?
It gets smaller.
It gets smaller again. Okay, so therefore, if that's right, then basically the derivative of this function should be really tiny, then peak at 1, and then be really tiny positive again. But it's always positive, certainly. Alright, so I claim that this is a pretty good graph. And that is, in fact, we've seen this function before. It's the witch of Maria Agnesi. It came up in the parametric unit. I won't give you the equation because we're about to discover it. But this is our guess for what the derivative of arctan. All right, we're doing this before the bell rings. Let's go. How are we going to discover the formula for the derivative of arctan? Well,
Tangent both sides.
yeah, that's right. This process of implicit differentiation can be used to find the derivative of any inverse function. I just write it as y equals arctan. And I set myself as the goal to figure out what dy dx is. Alright, well, I don't know how to differentiate arctan, so I need to write this in a different form. What's the different form I should write it in? Tan y equals x. Okay, now I have successfully rephrased this relationship between x and y in a way that involves things I know how to differentiate. So without further ado, we just differentiate both sides with respect to x. What's the derivative of x?
1.
Okay, moment of truth. What is the derivative with respect to x of tan of y?
Secant squared of something times dy dx.
Yes, the derivative of tan of something is secant squared something back inside dy dx.
Secant squared is 1 plus tangent.
In fact, this was just pretty chill, right? dy dx turns out to be
Cosine squared y.
cosine squared y. Okay, So that seems easy, but I don't want my formula to be y, because what is y after all?
Arctan.
Y is arctan. So the real answer to this is that dy dx is cosine squared of arctan. And even though you could leave it like that, that would be like gross to do so. So now the calculus is done. What we now need to do is do some pre-calculus. What is the cosine squared of arctan? Well, this is a pre-calc skill. There's a careful way to do it, and then there's a less careful way to do it. The less careful way is you just draw yourself a triangle in the first quadrant, because that's the best quadrant. And then you say, all right, how do I label the sides of this triangle in such a way that I'm making a picture of arc? What is arctan?
You take the inverse of y over x.
Yeah, arctan is just the angle whose tan is x, right? So what is the angle whose tan is x?
Theta. I don't know.
You just go x and 1.
Oh, yeah.
Okay, you can call that theta if you want. So I have just made a picture of arctan. Arctan x is just the angle whose tan is x. So that's arctan.
Oh, I see.
Okay, but if that's x and that's 1, does everyone agree that tan theta is x? Tan theta is x? Okay, what's this then?
Here, you could just use trig identity.
Root x squared plus 1? Of course. Okay, and now what's cosine theta?
X over, no, it's 1 over
1 over root x squared plus 1, agreed? Say agreed. Good, so what's cosine squared theta? 1 over x squared plus 1, right? And there it is, we're done. dy dx is cosine squared arctan. In other words, cosine squared of that angle, which is arctan, which is, therefore, the answer is
1 over x squared plus
1 over x squared plus 1. So we just derived the formula for the derivative of arctan, very important formula. And if I now go back and just graph y equals 1 over x squared, or sorry, plus 1, then you know exactly how to do this, because we did this back in the day, right? How do you graph 1 over x squared plus 1 if you're just like in pre-calc or something? You graph x squared plus 1, which looks like a parabola, and then you
reciprocate.
reciprocate it. And when you reciprocate it, what do you get? You get that. So our guess was right. Okay, so in some sort of perfect world, you would all now on your own like go through the remaining 5 pages of this packet following this precise order. Graph the trig function. Notice that it's not 1-to-1. Remind yourself what the conventional restriction is. Draw the inverse function. Look at it. Estimate the tangent lines. Guess what the derivative should look like. Then write it out as y equals. Undo it. Differentiate implicitly. Solve a pre-calculus problem. And then, okay, get it? This is like the way to learn the formula. All right, good. Screwed around for 35 minutes, then we went hard for like 50. I don't know if that was a popular decision. Say goodbye, internet.